Okay, so today we're going to go over some differentiation rules. Like we said, we had the derivative, which is defined as a limit, okay, as h approaches 0, f of x plus h minus f of x over h, or f prime of c is equal to the limit as x approaches c, f of x minus f of c over x minus c. So these rules come from really using this limit definition and generalizing to other types of functions. Okay, so although we might not be explicitly using these limits, okay, that's where these rules are going to be coming from. So keep that in mind. So the first one we have here is pretty simple here. It's just called the constant rule. Okay, constant rule. And simply says d dx. Okay, keep in mind d dx is representing the derivative of some function with respect to x, so the derivative of c. Okay, and I want you to think before I write it down what this answer is, the derivative of c. Keep in mind a derivative, yes, is a function derived from that limiting process. But ultimately, it is representing the slope of the function at a point, the slope of the tangent line to the function at a point, or the instantaneous rate of change of the function. So if we're thinking that way, we're thinking what's the derivative of c, a constant, right? This is a constant, 5 pi e -4 square root of 5, all right? What's the slope of that? Well, constant functions graphically a horizontal line. So if you think about that, well, 0. So the derivative of a constant is 0, okay? That's pretty straightforward. Then we get into the kind of first real rule that when generalized from that limit really makes things a lot easier, okay? So the power rule. So for the power rule, if n, okay, is a rational number, okay, so if n is a rational number, then we're going to say f of x equals x to the n is differentiable, okay, which means that we'll be able to define the slope at any x on the function. So the function is differentiable. And what we have here is that f prime of x will be equal to n times x to the n minus 1. Okay, so notice here, our exponent n, which is a rational number, down in front here. And then what happens is with their exponent from our function n, we drop the power by 1. Okay, so this is really that first rule that we have that really is going to make our lives here much simpler. You think about some of the problems I had you do with finding the limit, definition of derivative with x squared, x cubed, and you had to multiply it out and find your like terms, cancel stuff out. Now that has been generalized, and I'm going to put up a video of just so you can see that, but it ultimately generalizes to this statement here, okay? So let's look at how we use this, okay? Keep in mind here we have x to the nth power, and then here's going to be our derivative. So let's do a couple examples quickly. Okay, so the first one, our function f of x is going to be equal to x cubed, and I want to know what f prime of x is. What is f prime of x? So all we got to do is take here n, right? This is the value for n. N, where's it go? In front, so there's n, x to the n minus 1, right? Well, we're not going to write like that. We'd simplify it, right, as 3x squared. Okay, so that is the derivative of x cubed, 3x squared. Done. Simple. 2, g of x equals, in this case, let's go with the cube root of x. Okay, what's the derivative of the cube root of x? Now, if we did the limit definition for this one, it would be a pretty big mess here. But this rule makes this very simple. Sometimes you have to first rewrite it. We need to rewrite the function so it takes the form of x to a power. Okay. Well, the cube root of x as a power of x is x to the 1/3. So there's rewriting. We're going to have to rewrite sometimes. Now, g prime of x. What is g prime of x? Well, 1/3 in front, so 1/3 x to the 1/3 minus 1, which will be equivalent to 1/3 x to the negative 2/3. Now, that is correct, but it also is pretty standard to not leave negative exponents. So we can write that as 1/3x to the positive 2/3, or sometimes we might see it as 1/3 cube root of x squared. Okay. I mean, all those are correct. Okay. It's just usually a standard way we're going to write it either with the positive exponent or as a radical in radical notation. So there's the derivative of g of x, which is the cube root of x. Let's do one more here. Number 3. And this one is where normally we would have a mistake. We're going to use a little different notation here. Let's go with the Leibniz notation. So 1/x squared is our function. I want to know what the derivative of that is. Okay. And we could use prime notation. Okay. Y prime. In this case, I want to know what dy dx is. Okay. Means the same thing, just different notation. So let's get used to that. So dy dx. Now, a common thing here, as you're watching this is a no. No, don't do this. Okay, that the common derivative that I would first see is 1/2x. Okay, and incorrectly, what did you do? Well, you did this kind of part right in the bottom. You 2'd in front, dropped the power by 1, except this right here, 1/x squared, does not take the form of x to a power of n. This is what? This is 1/x to a power of n. That's not what the power rule is. So in order to do this one, we first have to rewrite x squared, 1/x squared rather, as x to a power of n. So 1/x squared is equivalent to x to the negative second. Now this here, okay, power rule is good to go, right? It takes the form of x to the n, x to a power. Okay, so now what do we got? Dy dx would be -2, right? X to the, make sure you're subtracting -2 minus 1, which is -2 times x to the -3rd. And like I said before, generally we're going to make that a positive exponent in the denominator. So 2x to the -3rd. Oops, don't forget the negative. -2 over x cubed. So there's a couple examples of the power rule. Okay, pretty straightforward, I believe. Moving on. So what is the slope of f of x equals x to the 4th when, let's go, at x equals -1, 2, and 3. Okay, so what's the slope at those values? Pretty simple question to answer here. In order to find the slope, when you see slope, think derivative. That's what slope is to us now. Slope is our derivative, so think that way. So in order to do that, we got to find f prime of x. Now this is super simple if you think about how you would do this using limit definitions. It'd take, I don't know, a couple minutes to find your f prime. Now, a couple seconds. 4x to the 3rd. Done. There's our derivative. So then, finding the slope at those respective x values, f prime of -1, f prime of 2, f prime of 3 is dependent upon your ability to correctly do arithmetic and order of operations. So we plug in -1, cube it times 4, -4. This is the slope of the function f at -1. or the slope of the tangent line to function f at -1. F prime of 2 would be, here, make sure this tells f prime tells me where to plug 2 in. Don't plug 2 into here. This is function f. F prime of 2 goes into function f prime. It's a name. Reference it as such. So f prime of 2 is 2 cubed, 8 times 4, 32. And f prime of 3, 3 cubed, 27. And 27 times 4 is 108. Okay, so there's our slopes there, which makes sense when you think about the graph. X to the 4th looks like a parabola, just flattens out a little bit in the middle and then gets steeper. So that's going to come here, flattens out a little more, touches 0, 0. Right? So it touches your origin there. And it makes sense when you think about the graph. Over here at -1, right? There's my point. And if I drew a tangent line there, we might think it's coming in here looking something like that. So that slope is -4. When I go over here to 2, okay, I'm further up here on the graph. Okay, at 2, I'd be at the point 2, okay, 2 to the 4th, which is 16. And if I think about the slope of that tangent line, I'd be something like that, right? It's steeper in a positive direction, okay? And then if I went over here to 3, I'm way up here off the graph, and you'd have a much steeper slope. So you can visualize that. Okay, so that's a little example of, the power rule and then using it to find slopes and such. Now this one, what is the equation of the tangent line to function f of x equals x of 4th when x equals -2. Okay, what's the equation of the tangent line to function f of x equals x of 4th when x equals -2? Now, problem solve. I'm walking you through it. Let's start to think, what do I need in order to find the equation of a line? Okay, to find the equation of a line, what do you need? I need what? To find the equation of a line, what do I need? I need point and a slope ultimately, right? That's the two things I need. I need a point and a slope. Now, maybe you have 2 points, in which case you find a slope, but ultimately you got to get a point and a slope. And if you think here, what do I have? Do I have any of that? Well, no, you have one of the ordered coordinates of the ordered pair. You have an ordinate, not a coordinate. But easily enough, I can find the value that goes with that. So my point, what's f of -2? F of -2 is 16. So now I have the point is -2, 16. So there's my point. And I need the slope. And I just said previously that when you see slope here, we think derivative. So I need the slope at -2, which means I need to know f prime of -2. In order to find f prime of -2, I need to first find f prime. So what is f prime of x? F prime of x would be 4x cubed from before we had that. In this case, f prime of -2, okay, is going to be -32. So this is what? That is m, my slope at -2. And now I have a point and I have a slope. To find the equation of a line, here we go. We have point slope form. Y minus y1 equals m times x minus x1. And we have y equals mx plus b, okay? So here, might as well use this one. So we get y minus y1, 16, equals m, -32, times x minus a -2, so x plus 2, okay? Now, listen to me. For those of you who are taking the AP test, you can 100% absolutely leave your line looking like that. There's no reason to do any more than that. That is the equation of the line, okay? You don't need to put it in slope-intercept form, okay? No reason to. Now, if you go ahead and put it in slope-intercept form, okay, and I'm telling you, for the AP, if you're taking the AP test, do not do that. The chance you're going to screw stuff up. So we have -32x We distribute the negative 32, we get negative 64 plus 16, which would be minus 48. Okay, and that would be our slope-intercept form, or right there. That doesn't help. If we look at that, the only reason a lot of times we put in slope-intercept form is because, in certain circumstances, negative 48, knowing the y-intercept, is something we want to know, okay? And the other reason really is that for a given line, all right, for any line, there is only one slope-intercept form. This is unique for any line. There's an infinite amount of point-slope forms, right? Because it's dependent upon a point you pick on a line, which is an infinite amount of them. Okay, so a lot of times that's why this is then becomes unique. So either one of these is the equation of a line. All right. Okay, moving right along here, we have the equation of a line, tangent line. Finish that one up. Let's move on to another rule here, which is called the constant multiple rule. Okay, so the name's not really important, but we'll put it down anyway. So the constant multiple rule, okay, this basically says if f is differentiable, okay, so if f is differentiable and, okay, c is a real number, then the derivative of this c, a multiple of f of x, right, the derivative of that is going to be equivalent to just taking that multiple c times the derivative of f of x, okay? Which makes sense if you think about graphically what happens when you multiply a function times some constant, it just stretches it out vertically, okay, which is going to make your slope steeper by that factor, all right? So how do we use this? Where does this pop up? Well, for instance, some examples here. If we had one here, y equals 5 over 2x cubed, okay, so 5 over 2x cubed. If I am to find y prime here, what's y prime? Again, don't just take the derivative of this x cubed in the denominator. We got to first think about rewriting. So this would be 5 over 2, 5 halves, times x to the negative third. Okay, so now here is the constant c. c times what? F of x. So now we have this constant multiple rule happening. And all you really got to do is take your n times what's in front. Okay, so negative 3 times 15 would be negative 15 over 2. X to the, drop the power by 1, negative fourth. And then you have y is equal to negative 15 over 2x to the fourth. Okay, so there's an example of using the constant multiple rule. All right, here's another one. We'll go with 2. Right quick, let's go with y equals 7 over 3 x to the negative second. All right, same thing, we already think ahead. That's going to be equal to 7 over 3 times x to the second. So then what's y prime? Well, we have 2 times 7 thirds, 14 thirds, x to the first. Done. Call it a day. And then the third one, right, y equals 5 over 2x quantity to the third. Right? Gotta be a little careful with this one. Okay, you can bring the 2x quantity to the third up. Okay, and then the mistake we would see there, I'm just going to go over off to the side a little bit, show you the mistake that you're not to make. Okay, so if we went off to the side and did, let's just look at this, 2x to the negative third. Let's say we brought that whole quantity up to the top. You can't take this exponent, pop it in front, and say that your answer is negative 3, 2x to the negative fourth. Okay, because why? This is not x to the third. This is 2x to the negative third, or negative third. This is 2x to the negative third. Okay, so we can't do that. There's going to be a different rule for handling that kind of thing later on. So what we need to do is first multiply out 5 over 8x cubed, 5 over 8x cubed, then rewrite that as 5/8 x to the negative third. Now this is what we need. A constant times a function of x. We could take the derivative. Y prime would be equal to 5 over 8 x to the drop the power by 1, negative fourth. Simplify correctly, 5 over 8x to the fourth. And that one, done. There's y prime. So that's the constant multiple rule. Simple enough there. Next rule. And this is just what we would call the sum and difference rule. So sum and difference rule. In this one, d dx, right? So the derivative of, here we have a function of x plus or minus either one, another function of x, right? That the derivative of that is going to be equal to f prime of x, and then plus minus g prime of x, okay? All this is essentially saying is that when you have things added or subtracted, you're allowed to take the derivative of each term separately, right? In this case, f prime and g prime, and then add or subtract the results after the fact, okay? Don't generalize that to other operations right now, okay? Does not apply, right, to multiplication division. There's going to be another rule for that. And, the similarity, the analogy is something like this. When we have, the square root of 4 times 25, right? Multiplication here. We're allowed, mathematically speaking, to do this. That's fine. You get 2 times 5 is 10. That's correct. Well, this doesn't generalize then to 4 plus 25, right? You can't take the square of this and say, oh, this is equal to 2 plus 5, 7. No, that's not correct. Don't do that, okay? So here it does generalize to addition and subtraction. So take the derivative of this function separately, then you could add or subtract the results. And where that pops up initially for us is situations that say we had f of x equals x cubed minus 4x plus 5. Okay. X cubed minus 4x plus 5. What's f prime? F prime of x, here we go. Function of x minus a function of x plus a function of x. So we don't have to do anything really fancy here. We just individually take the derivative of x cubed, 3x squared. The derivative of 4x. What's the derivative of 4x? This one, sometimes you try to do these power rules. There's no power rule for this. Think, this right here is a line. 4x. What's the slope of 4x? 4. That's what a derivative is. So minus 4, okay? You know what I mean? It doesn't make sense to do this. 4x to the first. 1 times 4 is 4. X to the drop the power by 1. X to the 0, right? That's 4. And then here, careful. What's the derivative of 5, a constant? 0. In which case, here, I'm done. F prime of x is 3x squared minus 4. Okay? So that's all there is to using this sum and difference rule. This is just, again, telling you that you're allowed to take the derivatives of the terms separately and then add or subtract the results. Here's rules that you got to commit these to memory. There's nothing fancy in terms of doing these. This is just pretty much rote memory. The derivative, I'm just going to write this one out like this. So your trig functions, the derivative of sine of x and the derivative of cosine of x. All right, what's the derivative of sine? The derivative of sine is cosine of x. And the derivative of cosine of x is negative sine of x. Okay, so that is just two derivatives you got to commit to memory, kind of like this one here in terms of, okay, I said note this as a fact. Hopefully, as you're watching this, you look at that and go, oh, I remember that is what? 1. Okay, so same thing here. Derivative of sine is cosine, derivative of cosine is negative sine. We'll get to tangent and some of the other ones after we go over some more rules. But initially, these are the introductory rules here. We went over some stuff with finding derivatives using the rules, finding the tangent line, problem solve a little bit. There's going to be times when you see problems, you're exposed to problems, you're asked to answer a problem. a question and you're not exactly sure, if you've never seen it exactly like that before, but you have the information you need to answer it, you just got to problem solve and say, "Hi, what do I need to get the equation of line? I need a slope and a point. Do I have a slope? Do I have a point? No, I don't have a point." And talk yourself through it. Ask yourself questions, answer those questions, and hopefully that leads you to the correct answer in the end. So watch this over, take notes on it. By all means, pause, rewind. Okay, make this Friday movie night type stuff. Let me know if you have any questions.